So before the presentation, please allow me to first introduce Professor Chen. Professor Chen is currently a professor at Peking University. He received his bachelor and master degrees from Tsinghua University and a PhD degree from Princeton University. His research focuses on the flame dynamics of fundamental combustion processes. Combining theoretical analysis, numerical simulation, and experimental measurements, he worked on challenging problems on ignition theory, accurate laminar flame speed measurement, and deflagration to detonation transition, and the detonation engines. He was awarded the Bernard Lewis Fellowship and the Hiroshi Tsuji Early Career Research Award from the Combustion Institute, and the Young Investigator Prize from Asia Pacific Conference on Combustion. He is a fellow of the Combustion Institute and is currently on the board of directors of the Combustion Institute and the Institute for Dynamics of Explosions and Reactive Systems. He serves as the associate editor of Combustion and Flame. So now I give the time to you, Professor Chen. If you are ready, please start. Thank you very much.
Okay. Thank you for the introduction and for giving me the chance to report our recent work on ignition process simulation using the OpenFOAM. So basically, actually, my work is mainly focused on the ignition physics instead of the software OpenFOAM. So here is the background of my research. Basically, I will talk about ignition. I should mention that the ignition here means that forced ignition instead of the auto ignition. You know that in shock tube experiments, people measure the ignition delay time. That kind of ignition we call the auto ignition because it's ignite at high temperature pressure automatically. Here we are talking about forced ignition using a spark. So this is the topic we are focused on. First, we look at why we should study ignition. This is one sentence copied from a recent paper by Poisson's group. He mentioned that the ignition of premixed flames is an ubiquitous problem in the field of combustion. Understanding mechanism, control ignition, and the determination of minimum ignition energies have been the daunting research topics over the last 100 years. So this means that ignition actually is a very fundamental combustion problem. It's also a very challenging problem. So let's look at what's the application of the ignition. For example, ignition is very important to control in the internal combustion engines and to develop a superlean combustion. So recently, to meet the challenge in the environmental regulation, people are trying to develop high efficiency internal combustion engine. In Japan, they have a program to have a target for the efficiency to reach about 50%. Basically, they use the superlean combustion because superlean combustion have a low heat loss to the wall and which can increase the thermal efficiency to 50%. However, if you have a mixture in a superlean condition, it's very difficult to ignite, especially when the mixture is near the flame limit. It's kind of difficult to ignite the mixture. So we need to understand the ignition at this kind of superlean conditions and to make sure that we can get a successful ignition for the superlean conditions. Another example is about high altitude relay injector engines. Injector engines, basically, if you have work on the high altitude conditions, and they have low pressure and low temperature, it's also very difficult to ignite. So you need to find some method to ensure that you can achieve successful ignition. The third application is about high-speed combustion. For example, in a scramjet. In a scramjet, actually, they have a very high-speed flow. So it's very difficult to ignite the mixture in a high-speed incoming flow. So you need to find some method to ensure that you can maintain successful ignition. The last example is actually try to avoid ignition. For example, in fire safety and in explosion, this kind of hot particle and this kind of accident hot spots can initiate ignition and the flame propagation. So we need to understand the mechanism for the ignition, and so that we can find effective ways to prevent ignition. So basically, this is the background for the ignition. So ignition is very important. And actually, there are many studies on ignition. This is a classical experiment on ignition. If you have two electrodes, a pair of electrodes, and there's a discharge, so this is a plasma kernel, and eventually it can be an ignition flame propagation. So assume that you can have a fuel mixture, and you have electrodes, and the discharge can get different ignition results, depends on the energy and also the mixture condition. If we plot the flame radius as a function of time, the first scenario is that you can see a decay ignition kernel. Basically, if the mixture is like below the inflammable limit, you cannot ignite it. Or if the ignition energy is too low, you cannot also ignite it. So this is the decay ignition kernel. The second case is that you have a stationary flame ball, which means that the flame kernel radius slightly increase, and at certain stage it will remain to be constant. And this kind of flame ball was only observed in microgravity experiments. And the third case is a self-extinction flame. The flame radius will increase continuously. At a certain stage, which will suddenly extinction. So the flame just disappear. So this is also observed in the microgravity experiments. And the last scenario is that the flame radius continuously increase with time. So you have propagating spherical flame continuously propagate out, and eventually you can get a successful ignition. So this depends on the mixture condition and the ignition energy. Basically, you have different outcomes from a spark ignition. So the question is that we are focused on how to get successful ignition, and we are interested in the minimum ignition energy that can help us to achieve successful ignition. So from the theoretical part, we are focused on two parameters. The first one is the critical length scale, and the second one is the minimum ignition energy. The question is that what is the control length scale for the flame ignition, and how it is related to the minimum ignition energy? Basically, if you read the textbook for combustion, there is a so-called thermal theory for the ignition. It was mentioned that flame thickness basically is the control length scale for the ignition. Why is flame thickness? It's based on the computation between chemical heat release generation and the conductive heat loss. If you have a successful ignition, which means that the chemical heat release should be higher than the heat loss. So basically, if you look at the Gaumont equation for the temperature, this is the heat conduction, this is loss, and this is the generation due to the chemical reaction. The critical condition, basically, they are these two terms balance. We know that the reaction heat release basically proportional to the volume of the ignition kernel, and the heat loss basically proportional to the surface area multiplied by the temperature gradient. And after some manipulation, we can get that the critical radius for the ignition is proportional to the flame thickness. So this is written in textbook. Minimum ignition kernel radius size is proportional to the flame thickness. And the minimum ignition energy basically proportional to the cube of the flame thickness multiplied by the temperature increase from the initial temperature to the adiabatic flame temperature. So this is a good estimation of the minimum ignition energy using the flame thickness. This also helps to explain that why high altitude ignition is difficult, because at high altitude condition you have low pressure. Low pressure will means that you have large flame thickness, and once you have large flame thickness, which means that the ignition energy should be large. So it's very difficult to ignite at high altitude conditions. But this theory is basically only focused on the heat loss and the heat generation. It doesn't consider the fuel consumption. So afterwards, there are some theory improvement on the theory. So there is a thermal mass theory based on the flame ball radius proposed by Theodorich and Diash and Zheng co-workers. And this basically assumes that the flame can be ignited when the ignition kernel size is higher than the flame ball radius. However, this theory didn't consider the flame propagation. So in the around 2000, people developed the so-called quasi-steady theory. They consider the ignition and the flame propagation. Basically, in the Gaumont equation, you consider there is a flame propagation term, and also the heat loss and the mass, and also the chemical reaction term. And recently, we also did some theoretical analysis to improve the theory. We included the unsteady term. basically this uncertain term that covers the so-called memory effect, and this memory effect will change the trajectory of the flame propagation and can affect the ignition energy. So this is a theory development. However, in the theory, there are several limitations. For example, usually theory assumes a spherical kernel. It's like a one-dimensional. It doesn't consider the electricity effect and also the geometry of the ignition kernel. So it also neglects the flow ignition interaction. Another part is that in the theory, we usually assume it's a one-step chemistry. So the low temperature chemistry actually cannot be covered in the theory. So the flow effect and the low temperature chemistry effect cannot be covered in the theory. How do we study these two effects? We can use with the help of simulation. Basically, we can understand how the flow and the low temperature chemistry affects the ignition. However, in the ignition simulation, there are many challenges. Actually, this was also mentioned in the last seminar given by Professor Su Yang. The ignition process is a multi-physics process. It includes plasma, shockwave, flow, and the transport and the reactions. And also, it's a multi-scale problem. In terms of time scale, it's kind of picosecond, nanosecond, microsecond, and millisecond. And in the length scale, it covers from micrometer, millimeter to meters. So, for example, if you look at the spark ignition, they have different phases. From the beginning, there's a pre-discharge phase, and there's a breakdown phase, and there's an arc phase, and there's a glow discharge. And these kind of different phases have different plasma chemistry and the reaction processes involved in this kind of processes. So it's very difficult to mimic, to reproduce all these phases in the simulation. If you look at the laser ignition, similar to the spark ignition, it covers a broad range of time scale from the initial laser pulse is in the scale of nanosecond, and the plasma emission is from nanosecond to the millisecond, microsecond, and the shockwave is around the microsecond, and the ignition delay time or flame kernel development is from microsecond to millisecond, and the combustion process and the pressure rise phase is about millisecond to second. So it's a very complicated problem with multi-physics and multi-scales. Actually, people are trying to use OpenFOAM to reproduce this kind of ignition process. This one is a work done by a France group. They didn't use OpenFOAM. They just proposed phenomenological modeling for the ignition process. For example, in their simulation, the nanosecond repetitive pulse discharge model they have this kind of discharge energy using different paths. For example, for the chemical energy, for the heating energy, and for the vibration energy to distribute it into the molecules. So it's a very complex problem. And in the last seminar given by Su Yang, about 1 week ago, he talked about using the plasma assisted combustion solver developed based on the OpenFOAM. They have two types of solver. One is based on reacting form. The other one is based on root central form. Basically, they want to simulate ignition in the incompressible flow and the compressible flow. They compile the control and the CVOD in their code. And also to give the detailed plasma modeling, they also use the passkey code, which was used by Professor Zheng's group in their recent work for the ignition simulation. So if you are interested in this kind of plasma ignition and the process, I think I refer to the seminar given by Professor Su Yang. And in my talk, basically, I will not talk about plasma stuff, and we only use the simplified ignition model to study the ignition process. So here is the solver we used. We use the EBI DS form developed by Torsten in KIT. Basically, this is their website. This is open source code, and this code is based on the compressible reactive flow solver. They can handle detailed molecular transport and thermodynamic models using control. And they have efficient chemistry computations. You have CVOD and automatically code generation for different chemistry, and also have load balancing, which have some very good polarization performance. It's a very excellent scalability and performance for reacting flow simulation. And the more details actually was given by the seminar about 3 months ago, given by Toaster. I think it's available in the YouTube. Basically, we use this solver based on OpenFOAM to study the flame dynamics, and also other people study this kind of hydrogen flame instabilities. So the details on the OpenFOAM, basically, I will skip, and I will focus on the physics of the ignition in my talk. And my talk basically consists of 2 parts. We are trying to answer 2 questions. The first one is, how does the flow affect ignition? We will talk to you about flow facilitated ignition. It's a kind of premixed flame. The second question we try to answer is, how does low temperature chemistry affect ignition? We have 2 paths. One is the ignition by a hot particle, it's premixed flame. The second one is the ignition in a mixing layer, it's a non-premixed flame. So let's first look at the first part on the flow effects on the ignition. First, let's look at let's have a question. How does the flow affect the ignition? In experiments, basically, people usually use the static mixture. We don't consider incoming flow to measure the ignition energy. But in the practical engines, actually, the inlet flow basically have some flow velocity that will push the ignition kernel away from the electrodes. So this kind of flow field basically affects the ignition kernel development and the ignition energy. This is some experiments, very recent experiment at Purdue University. They measure the ignition energy for hydrogen air at different bulk velocity. You can see that the ignition energy basically increase continuously with the incoming flow velocity. And also, this is very easy to understand. Basically, as I mentioned before, that there is a conduction heat loss. If you have a uniform flow from bottom to the upside, the flow will bring the convection heat loss. This is the convection term. And this kind of convection heat loss will increase the heat loss and then makes the ignition more difficult. That's why the ignition energy will increase with the incoming flow, because this term becomes larger, the heat loss becomes stronger. Also, people are doing experiments using the turbulence. For example, they have a mesh. This kind of mesh can generate turbulence, and they can modify the mesh turbulent intensity, this U prime. And their measurement finds that the mean ignition energy also increase with the turbulent intensity. They have 2 stages, but it's kind of monotonically increased. This is also very easy to understand, because if you have turbulence, they have a turbulent transport. Look at this formula. This is the heat conductivity. This lambda 0 means that the heat conductivity due to the laminar flow due to the random motion of the molecules. And the red part is the effective conductivity due to the turbulence, because the small vortices will enhance the heat transfer in the mixture. So this kind of turbulent transport will increase the heat conduction, and then therefore will increase the heat loss. So this means that the mean ignition energy will increase with the turbulent intensity. So it's very easy to understand. So the answer to this question is that the flow will increase the ignition energy, will inhibit the ignition. However, we have the question, does the flow always inhibit ignition? The answer is no. Turbulence actually sometimes can facilitate ignition. It can help the ignition. This was found by Professor Law's group about 8 years ago. They have a paper on PRL. Basically, if you look at this figure, this is the ignition energy, and this vertical axis is the root mean squared flow velocity, turbulent velocity. Basically, you can see that in certain regime, you can get a successful ignition in this triangle regime, but you cannot get ignition at this part, which means that some kind of flow can promote ignition, because at the same ignition energy, you can get a successful ignition with flow, but ignition failure without flow. Another experiment was done by Professor Stephen Shah in Taiwan. He also measured the mean ignition energy with the turbulent intensity. You can see that the mean ignition energy basically first slightly monotonically decrease with the turbulent intensity, and then will increase. So in this regime, you can see that the turbulence actually can promote ignition. That is in contradiction with our argument just now, because we mentioned turbulence will increase the heat loss and make the ignition more difficult. However, the experiment found that ignition can be easier with the turbulence. So the question is, why the ignition? And actually, they only found for the mixture with large Lewis number. For example, for rich hydrogen, the Lewis number is 0.2 to 0.2, and for the hydrogen air, the Lewis number is about 2.3. So the experiments basically show that the mean ignition energy will decrease with the turbulent intensity for certain conditions, and the weaker turbulence basically promotes ignition for the Lewis number larger than 1 for rich hydrogen air and the lean isooctane air. So this is kind of difficult to understand. Actually, even this experiment was done about 8 years ago. People are still working on how to explain this phenomenon. So why the turbulence can enhance the ignition and help ignition? There are some explanation actually. For example, Professor Stephen Shai, they give the explanation as this. They think that when you have a turbulence, the flame kernel will have this kind of deformed surface. And in some local position, actually it's negative stretch. And if you look at the stretch, basically this is the definition of flame stretch. And the stretch effect on the flame can be approximated by this formula. So it's the Zeldovich number multiplied by the Lewis number and the stretch. And if you have the positive stretch and you have Lewis number larger than 1, this part is negative, this is positive, which means that this is negative, which means that this kind of stretch will inhibit the flame propagation. However, if you have a negative stretch, this kind of negative stretch and the larger Lewis number, this is negative, this is negative, so this sigma becomes positive, which means that the negative stretch can promote ignition. So they think that the turbulent facility ignition only occurs for Lewis number larger than 2, because this part, this is Lewis number larger than 1. And the negative stretch actually helps to achieve the successful ignition, because this kind of negative stretch and the Lewis number larger than 1 will promote the local ignition kind of from propagation. So this is their explanation based on the flame coverage and the flame stretch. However, this kind of experiments was never repeated by simulation. So this is some simulation done three-dimensional direct simulation on the ignition in a terminal flow. So the top line is ignition in a flow velocity is equal to 0. So it's laminar flame propagation out. But in these bottom two columns, basically there is a flow turbulence in affects the ignition front. We can say that the turbulence always inhibit the ignition. So the TFI, to turbulence facility ignition, was not observed in three-dimensional direct simulation. So the simulation never repeats this kind of experiments. So we are wondering why we cannot repeat the experiments. So this motivates our work. Basically, we want to assess the effects of uniform flow on the ignition kernel development. We don't want to study the turbulence, because turbulence is a very complicated process. It has many factors to affect ignition. We just simplify a problem to use the uniform flow. And we actually found that the flow facility ignition use this uniform flow actually has similar physics as the turbulence facility ignition, which I will talk to later. So this is our model and the method. Basically, we can see hydrogen air mixture at room temperature and pressure. We do the 2D and 3D simulation. If you 2D, basically for a static case, there is no flow, it's an asymmetrical process. But for three-dimensional, we have a vertical flow to the electrodes, and this kind of ignition kernel will push downward. So it's not asymmetrical. We need to do the three-dimensional simulation. And for the ignition part, actually, we use a very simple model. We just add the energy source term in the energy equation. This is the ignition energy acquisition. We have this is the cross surface area pi RE square, and this d cap is distance. So this is the volume of the ignition kernel, and this is the time duration for the ignition energy depletion, and this is the energy density for the ignition kernel. We have the electrode radius basically is fixed, is 0.32 millimeter, and the gap distance we can change, and the energy duration for the depletion is about 0.2 millisecond. And we use the EBIDS OpenFOAM based on the OpenFOAM developed by KIT. And the more details actually can be found in our recent paper published on the Combustion Symposium. So basically, this is the first result on a quiescent mixture. We don't consider the incoming flow. They have different stages. So first, you have energy deposition, the temperature will increase, but there is no chemical heat release. Because the chemical heat release, they have some auto-ignition delay time. And after about 0.2 milliseconds, you have this kind of heat release. And this kind of heat release will generate an ignition kernel. So basically, this is the ignition kernel front. It's asymmetrical. And eventually, the kernel will propagate out. And you can see that around the electrodes, actually, the flame is quenched, or the flame is very weak, because these have very large stretch or curvature. And also, there is a heat loss to the electrodes, which will quench the local flame. So this figure basically shows that you have this kind of two stages. First is auto-ignition to give the chemical heat release. And the second stage is the flame kernel should propagate out to be a self-extinction flame. And then we compare the different scenarios for the ignition. This one is, we consider the different sequence ratio. This is the top line basically is the reference case. We have a rich hydrogen air, which have a large Rees number. The gap distance is fixed to be 0.64 millimeter, and the ignition energy is 1.24 millijoule. So the left figure basically shows that if you reduce the sequence ratio to 0.4 from 5.1, you can see that the flame can be propagated out to get a successful ignition. It's easy to understand it because you have low sequence ratio, which means that you have a low Rees number. And the low Rees number basically means that the ignition energy actually is pretty small. So this is because the low Rees number reduces the ignition energy. At a high sequence ratio, you have Rees number about 2.3. So the flame ignition kernel just quenched. Another way to achieve successful ignition is just you can increase the gap distance. For example, if the gap distance increased about close to 4 millimeters, actually for the same ignition energy, you can see that ignition kernel can successfully propagate out. This is because at a large gap distance, basically the heat loss to the electrodes are greatly reduced. And also the flame curvature and the flame stretch is become smaller. Also, these two facts also promote ignition. And the third way is just make the wall to be adiabatic. Of course, this only achieved in simulation. So if you consider isothermal electrodes, they have a flame quenching, ignition failure. But for the adiabatic case, basically the flame kernel can propagate out waterly successfully. So this means that the heat loss to the electrodes is very important. And it can, if you can reduce the heat loss to the electrodes, it will help to promote ignition. So based on this knowledge, we next to study the flow effect on the ignition kernel propagation. This has three cases. This is a fuel lean case, and this is a fuel rich case, but a larger gap distance. And this is a fuel rich case at small gap distance. If you have a fuel lean case, actually the incoming flow fixed to be 3 meters per second. It will make the ignition kernel cannot be ignited because the incoming flow actually enhance the convective heat loss, so it makes ignition failure. If you have a larger gap distance, actually it also cannot ignite the mixture because the large ignition, even the large gap distance reduce the ignition heat loss to the electrodes, and the flow actually cannot help to reduce furthermore the heat loss to the electrodes. Only for the case C, for the rich case, actually this was done in the experiments for the turbulent assisted ignition. Only for the fuel rich case and the small gap distance, you can see that the flow can move the ignition kernel away from the electrodes and can greatly reduce the heat loss. So that's probably the reason that we can achieve that flow facility ignition. Because in the experiments, actually the turbulent facility ignition only occurs at a small gap distance like this, and only occurs at a large Rees number. This is also a large Rees number for the rich hydrogen air. It's about 2.3. So basically, this simulation is consistent with the experiments. So it shows that this is more details about it shows the flame front propagation. So if you have this kind of incoming flow, the volume for the top ignition kernel and bottom ignition kernel actually change a lot. We have this kind of downside ignition kernel, actually the volume is much larger than the upside ignition kernel. It will bring the symmetry, and more importantly, it will reduce the heat loss to the electrodes, and then it can make the ignition kernel stronger. And also, if you look at the curvature, here is pretty large, but here you can see this part of the curvature much smaller. This means that this reduce in the curvature can also enhance the ignition. So there are two reasons that we can get the flow facility ignition. Basically, the flow can push the ignition kernel away from the electrodes to reduce the heat loss. It can also change the shape, the geometry of the flame front, and to reduce the stretch effect. And in the experiments, basically, you can see that the turbulent flow can also move the ignition kernel some away from the ignition electrodes. So this is similar to this simulation for the uniform flow. So basically, we explain why we can get flow facility ignition. So in the turbulence, people use the negative stretch to explain the ignition. For turbulence facility ignition, we think this is not fully correct. You also need to consider the electrodes effect. Actually, in recent experiment by Professor Shai's group, they also conducted the ignition using laser. They found in the laser experiments, they cannot observe the turbulent facility ignition, because in the laser ignition, you don't have the heat loss to the electrodes. So the main conclusion is that for the turbulent facility ignition, it's not caused by local negative stretch. Actually, the heat loss to the electrodes, we think is very important. For the flow facility ignition in our simulation, we show that the reduction in the heat loss to the electrodes and the reduction in the global curvature basically explains that why the flow can facilitate ignition. And this kind of flow facility ignition has a similar mechanism as the turbulent facility ignition. And when Professor Shai read our work, he sent a message that he thinks that we have done the first simulation and approximation for the understanding of this kind of turbulent facility ignition. And in previous simulation, actually, there is no work to explain this kind of phenomenon. So this is the first part on the ignition due to the flow effect. Then I will move to the second part on the low temperature chemistry. First, we look at the ignition caused by hot particle. So let's look at the background. For the hot particle ignition, actually is important to the aircraft safety, because if you have lighting to have some hot spots, and it can give this kind of accident. And in the manufacturing, actually, this hot particle can generate like ignition process. So people are working on this kind of ignition energy for different mixtures and different particle size for methane, for hydrogen, and at different particle size. They have experiments, simulation, and recently we also conduct some theory. However, in all these kind of experiments, they didn't consider the low temperature chemistry. For example, for the electric hydrocarbon fuel in jet fuel, they have low temperature chemistry. So we want to know how temperature chemistry affects ignition. For example, if we look at this kind of scenario, if you have a hot particle, we have high temperature, about 1100 K, and the room temperature is, let's say, about 300 K. Actually, the ignition doesn't happen in the surface, because even the surface has a high temperature, but the surface, the temperature is in the NTC regime, means that there's some place which have the highest temperature in the NTC regime because the low temperature chemistry. So the ignition might happen some distance away from the surface. So we use this kind of one-dimensional and two-dimensional simulation to study how the low temperature chemistry affects this kind of particle ignition. So the first scenario is we just consider one-dimensional case, which means that there is no inlet flow. Everything is static, so it's a spherical symmetrical problem. We just do one-dimensional simulation. Here is the radius, and here is the time. The particle radius is about 1 millimeter. Radius is 1 millimeter, so this is the particle side. And here is the heat release rate counters. We consider this is the particle temperature is 1300 K. You can see that there is a weak heat release rate, which is corresponding to a core flame. And then on the surface, there's a hot temperature chemistry induced ignition, because the temperature actually, heat release actually is much higher than this part. And we also calculated the propagation speed. We found the cold flame is pretty slow. It's only 6 centimeters per second, but the hot flame actually is about in the order of 1 meter per second. So the hot flame is actually much faster, and eventually the hot flame can catch up and merge with the cold flame. And in this simulation, we consider the low temperature chemistry. If we remove the low temperature chemistry, we found that you only can get a hot flame. This means that there is no cold flame, and we can also calculate the ignition delay time for the different particle temperatures. We found that the low temperature chemistry actually greatly reduce the ignition delay time, because this kind of low temperature chemistry actually can accelerate the ignition process and then thereby reduce the ignition temperature. So this is a one-dimensional case, and we also consider two-dimensional case. There's a uniform incoming flow from the bottom side to the upside. And you can see that this is the flow velocity is small, it's 0.15 meters per second. Here, this right side basically shows the concentration of CH2. The left side shows the temperature. You can see that the right side, this ABC, this curve basically is a cold flame, because the temperature is below 1000 K. And you can see there's a lot of CH2 produced, which is due to a low temperature. But on the surface, actually, the temperature will increase to 1500 K. Actually, this is the high temperature chemistry induced. So there is a cold flame probability outside, and also it's a hot flame probability from inside to the outside. And eventually, the hot flame becomes pretty large, and the cold flame is still outside. But the cold flame speed is much smaller than the hot flame speed. So eventually the hot flame can catch up and merge with the cold flame. So there is only one hot flame can be observed. This is for low flow speed. And if you increase the flow speed, actually you can see that the hot flame can be pushed away from the ignition particle surface. And eventually there is only one cold flame on the two sides of this kind of particle. So this is the trajectory of the flame front. So the left side figure shows that if you have small inlet flow velocity, basically this kind of cold flame front will be propagated out, but eventually it will merge with this hot flame, and it will be consumed by the hot flame. So there is no cold flame. But for high flow velocity, actually the cold flame can always exist. And we also found this kind of non-monotonic change of the flow velocity on the on the ignition delay time. Basically, on this side is so-called the flow can promote the ignition, because the inlet flow can reduce the ignition delay time. This is not the same story as the electrodes case, because the electrodes you have heat loss. Here we don't have the heat loss. Actually, this kind of promotion due to the flow effects on the ignition is due to the boundary layer development at a different flow speed. So this is on the hot particle, basically pre-mixed flame. We also look at the ignition in a mixing layer, which is a non-pre-mixed flame. We want to know how the low temperature chemistry affects the ignition in a mixing layer. Actually, for the non-homogeneous ignition, they have broader application. For example, in the engine, you have a jet of the fuel injected into hot air, and there's some local ignition, actually it's non-pre-mixed ignition. And in the internal combustion engine, actually people can see that there's a cold flame induced during the injection, and there's a cold flame front propagation. So, however, there is no study on how the low temperature chemistry and the cold flame affects the ignition of the non-pre-mixed flame. So this motivates our work. Basically, we want to know how does the low temperature chemistry affect the forced ignition in a mixing layer, and we want to know how the cold flame evolved in a hot flame. So basically, our model is a mixing layer. In the top is the dimethyl ether, and in the bottom is the air. And the mixing layer we fix about 2 millimeters. And in the center we have a hot spot, and it's an asymmetrical problem. The hot spot basically have a fixed radius about 0.5 millimeters. And if we change the temperature of the hot spot, we can get different ignition scenarios, which will be introduced later. So basically, this is we change the ignition temperature of the hotspot from 800 K to 2000 K. The top figure shows the mixture temperature is at room temperature, and the bottom figure shows the temperature of the mixture initially is at 450 K, and the temperature is 5 atmosphere. And in the top figure, we only can observe the hot flame at a high ignition temperature, and no ignition failure if you have a temperature lower than some critical value. But if you have elevated temperature and pressure, you can see that we can observe the hot flame, warm flame, and the cool flame different scenarios. For example, for the temperature 800 K, basically, we can see this kind of cool flame can exist. But for the temperature about 1200 K, we can observe the warm flame. And actually, the cool flame can transit to warm flame and hot flame, which will be discussed later. So this is the maximum temperature and the displacement speed as a function of time for different cases. This is high temperature and pressure, and the ignition temperature 800 K. You can see that there is a slight increase of the temperature around this stage, and this means that there is a trigger of the core flame, because this is a low temperature heat release induces a small increase of temperature. So this regime is a core flame, actually around 20 milliseconds. You can see this kind of heat release rate, the temperature, and the out radical and the CH2. You can see there the lot of CH2 are produced basically due to the low temperature energy. And the flame the temperature of the burned gas actually is about 800 K with the core flame. And eventually there's a jump to a warm flame stage. So the temperature will have a second stage heat release eventually, and it go to a hot flame. So this is the initiation of the core flame from 28 milliseconds to 30 milliseconds. You can see that the stage that the heat release become much stronger, and the H2 can be gradually produced, and the actual temperature will increase to around 1000 K. And furthermore, if you have time larger than 30 milliseconds, it will evolve into a hot flame, because the core flame stage, the warm flame stage actually is very short. This is the warm flame stage. Eventually, it will evolve into a hot flame. So the hot flame will catch up with the leading core flame and evolve into a very complicated triple flame structure, like this one. Actually, this part is still have some core flames. So this basically shows that you have different stages. You have like a core flame and a warm flame and a hot flame. This is similar to a homogeneous ignition process. And if you change the mixing layer thickness, you can have some effect on the core flame development. Also, if you change the hotspot size and change the position of the hotspot, it also affects the ignition, because this mixing layer have different value of the mixture fraction. At the bottom is air, at the top is dimethyl ether. Actually, in the top side, actually, it's more easier to get a core flame. In the bottom side, it's more easier to get the hot flame. So different ignition modes can be achieved while changing the temperature, size, and the position of the hot flame. And we also analyze the displacement speed. Basically, consists of reaction and diffusion. And we also decompose the diffusion path into normal diffusion and the tangential diffusion. We found that the flame is balanced by the reaction and the diffusion, which means that it's actually the self-sustained flame. It's not an auto-igniting it's not an auto-ignition process. It's a flame because the diffusion balanced by the reaction. Also, we found that the diffusion in the tangential direction is very important. So it's a kind of partial premixed flame instead of diffusion flame. So we found this is a self-sustained partial premixed flame. And for the premixed flame part, we found that it's the flame propagation speed, the displacement speed actually change linearly with the stretch. We can get the masking length for the core flame, which is a very important parameter to correct the stretch effect on the core flame. And we found that interesting that the core flame speed is not sensitive to the pressure, because for the hot flame, actually, you have high pressure, you have low flame speed. But the cool flame actually is not very sensitive to the pressure. This is because the low temperature chemistry actually is not so much pressure dependent. So with that, I finished my talk. Basically, I have mentioned that the simulation of the ignition using the OpenFOAM developed by KIT's group. It's called EBIDS OpenFOAM. And we use only simplified ignition model. We just use some energy deposition for the energy equation. And then we coupled with flow and chemistry to study the different ignition process to understand the fundamental physics on ignition. So basically, we answered two questions. The first one is how does the flow affect ignition? We found that flow can facilitate ignition because the flow blows the ignition kernel away from the electrodes and reduce the heat loss to the electrodes. And also it changes the curvature, so it can improve the ignition. This actually helps to explain the turbulent facility ignition observed in experiments. The second question we answered is how does low temperature chemistry affect ignition? The first part is on the hot particle ignition. We found that low temperature chemistry can greatly accelerate the hot temperature combustion chemistry at certain range of the hot particle temperature. And for the mixing layer, we found that the three-stage ignition process can be observed. It consists of cold flame, warm flame, and hot flame evolution, which is a very complicated process. So that is my summary. And at the end, I would like to acknowledge my students, Chen, she's here, Yiqing Wang, he's here, and Dehan Yu and Schumann. They basically work on this kind of ignition stuff. I also would like to mention Zheng because he is the first one studied using the OpenFOAM to do simulation in our group. Now he's in Australia. And Wang Han, he also helped us to do the ignition for the flow facility ignition. He moved back to Peking. I would like to also acknowledge we are collaborators like Torsten, Peter, and Professor Bockham at KIT. And we have good collaboration with another group in Germany. This is Hannes, Anna, and Professor Christian Hassen at the TU Darmstadt. So with that, I would like to thank you very much for your attention, and I'm ready to answer questions.
Okay, thank you very much, Professor Chen, for your very interesting talk. So in the following, we will have the Q&A session. So if there is any questions from the panelists, so please unmute yourself and directly ask towards Professor Chen. Okay. So now we have two questions from the audience. So I will read the questions. Okay. Yeah. So the first one is the method of patching a specific region to a higher temperature is it a good strategy for numerical ignition modeling when the inlet total temperature is low? Yeah, this is the first question.
Okay. So the question is about to change the temperature, just use a hotspot. It's a very simplified method to achieve the ignition. As I mentioned before, actually for the ignition process, it's very complicated. You have like a plasma, you have a generator, high temperature, as well as a lot of radicals. And people also consider radicals affect ignition. To do the quantitatively comparison, it may be difficult to compare this kind of simplified hotspot method with experiments. But for the understanding the physics, I think it's enough to understand the process, use a simplified hotspot just to use the higher temperature to mimic the ignition. Basically, we just neglect the very complicated physics before the temperature increase.
Okay, thank you very much. And the next one is from the same audience. So does the ignition energy, duration, and the size of the ignition cells of the mesh affect the overall combustion results? He means does the properties of the hotspot have influence on the calculations? Suppose if we deposit more energy, ignition energy than required in the CFD domain, the sequence of the chemical reaction mechanism would be changed right from the chain initiation progression to the termination.
Okay. So basically, the ignition energy and the duration basically affects the results. For example, ignition energy, you have high ignition energy, you can get a successful ignition, but a low ignition energy, you can get ignition failure. And also, the question is pretty good. How does the duration of the energy deposition affect ignition? The answer is yes. Actually, they have some optimized duration for the energy deposition. Here, we only fix the duration about 0.2 millisecond. because we found that for Lewis number larger mixture, the optimum value for the energy deposition is 0.2 millisecond. Actually, if you have a very longer duration for the energy deposition, you need a much larger ignition energy to get the successful ignition. So this kind of duration certainly definitely will affect this kind of ignition process. And the question also mentioned about the
property of the hotspot.
The property of the hotspot, yes. The property, for example, if you have a very sharp or very smooth hotspot, it will affect the heat loss to the surrounding, which means that it also affects the ignition, especially the critical ignition energy and the initial ignition kernel development. And actually, in our simulation, we cannot go to very high temperature, like a temperature about more than 100 K. 100,000 K. It's like a plasma chemistry. We cannot, so we use the temperature actually is much lower than that one. But this definitely will affect the initial kernel development.
Okay. Thank you very much. So the next question is more general. So how would this ignition process change for multi-component surrogate fuels?
That's a good question. Actually, for the multi-component, here we only consider single fuel like hydrogen or dimethyl ethyl. We actually found that if you have like multi-component, for example, you're blending dimethyl ethyl with hydrogen, it will change the ignition because especially for hydrogen, the dimethyl ethyl, they have totally different diffusivities. And this kind of diffusivity will affect the ignition because the ignition kernel development is strongly depends on the Lewis number of the mixture, the different species for the hydrogen and for the dimethyl ethyl. So for this kind of very different fuel structure, fuel blending, you have very strong effect. However, if you have like a PRF fuel for the gasoline, like isooctane and heptane, actually the effect is not that strong. We found that for post ignition, the ignition energy for the heptane and the isooctane actually is pretty close. It's not like the auto ignition delay time. Auto ignition delay time, you can see that heptane and isooctane have very different results. But for the mini ignition energy, because they are mainly controlled by the transport, heptane and isooctane actually has very close Lewis number. So that influence is not that large. So we are expecting, depend on the fuel blending, you will give different results.
Okay, thank you very much. So next question is from the audience is, do you still keep mixture as pre-mixed for the analysis of mixing layer effects on ignition? I think this is for the last part of the presentation.
No, actually for the mixing layer, it's not pre-mixed. We have on the top side is the dimethyl ethyl, and on the bottom side is air. So there is a mixing layer. We have some kind of parabolic distribution with dimethyl ethyl and air. So this is the pure air, and this is pure fuel. So it's not pre-mixed. Actually, in this part, some regime they have some kind of pre-mixedness.
Okay. Thank you very much. So Professor Chen, can I ask you one question?
Sure.
Yeah, so for the turbulence effect, you mentioned the stretch rate actually important, right? So yeah. Do you have any comments about the turbulence properties, okay, such as like, scalar dissipation or the local, the turbulence intensity, because very strong fluctuations of the reactive scalars near the spark will also affect the, the ignition behavior, right?
Mm-hmm.
Yeah.
Yeah, basically, if you look at the right figure, I should mention that, emphasize that turbulence eventually can inhibit the ignition. Only in a very narrow regime, this regime, turbulence promote ignition. But if you have very strong turbulence, it always inhibits the ignition. So as you mentioned that the scalar dissipation becomes pretty large, actually the heat loss will become much larger. And that kind of effect will be dominate. So it's will promote ignition. But only in this low turbulent intensity regime, you can you get this kind of turbulent facility ignition.
Okay. Thank you very much. So any questions from the panelists?
Professor Chen, thank you very much for your very interesting talk.
Thank you.
I have one question. It's about the cool-film speed and how do you calculate it? Because when I do it, I found first, if the ambient temperature is relatively high and the transition from cool film to hot film propagation will be very quick. So it's very hard to get the cool film speed. And for your case, and I want to know how do you calculate from the post process, or you do it in the 1D or 2D simulation? In the 1D freely propagating flame case, or in other cases?
Yeah, thank you, Professor Zhang, for the question. That's a very good question. For here, we only reported results for mixing layer two-dimensional simulation. As you can see in this figure, this is the temperature evolution change with time. You can see that there is a broad window for the core frame development. This is after core frame, and the core frame will sustain, and in this kind of rise is the warm frame. So you have like about 20 to 30 milliseconds. So you have enough time to involve this kind of core frame. If you have some cases, the core frame lifetime is very short. Actually, it's very difficult to calculate the frame speed. So in our simulation, basically it depends on the case. Like we have this kind of temperature and pressure. We found that you have a broader window to make sure that the core frame can propagate. And this propagating process is pretty long enough, so we can calculate the core frame speed, use this kind of displacement speed. So this is actually we use the SD, and because this regime is pretty long, we can see this kind of evolution. This is the evolution of the core frame, because when the core frame expands, actually the curvature and the stretch will decrease. So it's propagating this way. This is for 2D simulation, and we also conduct a one-dimensional simulation. In a similar case, just a spherical frame. If your core frame is long enough, you have enough time to propagate, you have this kind of frame speed can change with the stretch rate. And actually, Professor Zhao in Tennessee, he also doing this kind of similar simulation. So you should select the condition to make sure that the core frame have enough time to survive. Otherwise, the core frame just merged with the hot frame. You don't have time to track this kind of trajectory.
Okay, got it. Thank you very much.
Thank you.
Okay, thank you very much. So now Boson and Thorsten raise a hand. So who wants to go first? Maybe Thorsten. Yeah, please.
Sure. Thanks for the nice presentation. I think the results of the flame stretch in turbulent flow affecting ignition are very interesting. But you mentioned also low pressure ignition at higher altitudes, where you have very large flame thickness. And of course, classically, the flame stretch is defined on a 2D surface. So when you have a very thick flame, then of course you have very strong 3D effects throughout the flame front. Do you think flame stretch is still a good measurement in these situations?
You mean low pressure?
Yeah, exactly. So when the flame's thickness is very large, because then the flame stretch might vary significantly depending on if you are towards the burn side or the lean side. So I'm wondering if there's a different quantity maybe that's better suited in these extreme circumstances.
I see your question. Yeah, for the low pressure case, the flame thickness becomes much larger. Basically, actually, the flames, the stretch or the maximum length is very sensitive to the counter to define this kind of value. For example, the stretch, the maximum length for the unburned gas actually can be totally different with that for the burned gas.
Right.
So there is this kind of effect. Even for even for normal pressure, this is also true, because you can select different temperature counters. But for this kind of effects, for the turbulent effects effects, basically, if you look at the local stretch, even at low pressure, you have very thick zone. I think should be the same effect, because use this kind of formula.
Yeah, I think it's a very interesting problem because I mean there are the strong stretch effect formulations which take more the mass change instead of the surface area change into account. But I'm not sure if this would be better. So I think this might be a interesting case to look at this more in detail.
Yeah, I think people use so-called mass-balanced, mass-based stretch rate, DeGoey,
Exactly.
DeGoey. Yeah, that
right.
interesting because you need not only consider volume surface, but also consider they have
right. Yeah. So maybe for the low pressure cases, this might be an interesting thing to look at some.
Yeah, I think so.
Thank you.
Okay, thank you. So, Boson, you have questions, right?
Yes. Hi, Professor Chen. Thank you for your talk. I have two small questions. The first thing is about the ignition, how to initialize your spark, or what other energy sources at the beginning. How to ensure the energy and also the size of it equivalent to what you want.
Okay.
Is there any magics? The second magics maybe is about initialization. How do you usually initialize your case? Maybe you can take one example. I think this is very sensitive. The ignition phenomenon is very sensitive to the initialization. And for the initialization, you will have some problems of the stability of the solving process at the beginning of your simulation. And can you give some advice? Yeah, thank you.
Okay. Actually, the ignition process is very complicated. I think you listened to the talk by Professor Yang. They have this kind of plasma generation, and actually the flame front is kind of like this kind of tornado shape. This is the frame is actually curvature and stretch is very complicated. In our simulation, we just neglect this part because this kind of stuff is the small plasma channel development eventually will give a spherical frame. So we are doing very simplified model. We just add the energy term in the energy equation, and we use this term in the energy equation. And this term will be activated at a certain place, which have a radius, like in this red regime, you have energy deposition. And the energy deposition only happens from time equal to 0 to time equal to 0.2 milliseconds. So we multiply by the time, multiply the volume and the energy density, we can get the energy. So initially the temperature is room temperature. Due to the energy deposition, the temperature will increase because you have a source term in the energy equation, which will increase the temperature. And eventually you have a hot spot inside. So this is one method, just use the source term in the energy equation. Another method is that we use the simplified hot spot here. So we just add the system, no system. So there is no system in the energy equation, but the initial condition is not like the one before. Initial condition that outside the hot kernel is room temperature or like some temperature, but inside the ignition kernel, which have radius of 0.5 millimeter, the temperature is, let's say, it's about, for example, this case is 1200 K. You can change this kind of hot temperature. So it's just the initial condition to get a hot spot. It's a simplified process. We don't consider plasma. Yeah, you are correct. I think the initial plasma kernel, especially if you have very strange shape, it will definitely affect especially the core flame, hot flame propagation. But here we only just consider simplified case.
Okay.
Yeah.
Okay. Okay. Boson, you have more questions?
No. Thank you. Okay,
thank you very much. So, any more questions from other panelists or audience? Maybe I ask one more. So for the solver coupling, right? We couple the Cantera and OpenFOAM. So where actually, is the chemical integration done? So in Cantera or in OpenFOAM? Because normally, OpenFOAM can also do the chemical integration, right? Chemistry integration, right?
Yeah, that's a good question. Actually, I cannot answer. I think Chen probably can answer this question.
Okay.
Okay. Yeah, maybe I can quickly answer this.
Yeah.
So yes, OpenFOAM has its own ODE solvers.
Yes.
And if you run the EBDNS form code and OpenFOAM, you will get the exact same results. But we are directly calling the CVODE solver by standards. So we are not going through Cantera, we just directly from the reaction rate computations, we call the CVODE solver. And this is for two reasons. So this is faster than what OpenFOAM has with its own ODE solvers, and also more robust. So in OpenFOAM, you can run into cases where your simulation just diverges, but CVODE is very stable and very efficient. So this is why we directly call it CVODE.
Okay. Okay, I understand. Okay. Okay, thank you very much. Okay. Yeah. So any more questions? Okay. So if no more questions, we open the camera and thank our speaker, Professor Chen again. Okay. And also happy Mid-Autumn Day. Okay. Because tomorrow is a Mid-Autumn Day in China. Okay. And also Teachers' Day. Okay. Yeah. So happy holidays. Okay.